Hi, welcome everyone. Thank you for attending the session. My name is Jorge Elizondo. I'm the CTO and one of the co-founders of Heila Technologies, and I'm very grateful to have been invited to present in this Linux Foundation Energy Spring Summit, and to have the opportunity to talk about Heila, the company that I've been working on the last 5 years and I started. Um, and to tell you more about what we do as a company, some of the projects we have done, and where there are some opportunities for a more open source collaborative approach regarding microgrids and distributed energy resources. So Hela started in 2015, and it was the result of a combination of having some academic experience. Back then, I was doing my PhD at MIT on microwave control, microwave analysis, trying to understand these systems. And I was also participating in microgrid projects, especially in a microgrid project in California, which is called the Stone Age Farm, where I was participating, trying to build a control system. So I was able to learn firsthand the challenges of building systems in the field, and compare that to the academic knowledge of how things should work. And I saw a big disconnect. And that's how Halo started. And we started a company with a mission of transforming the energy industry, and build it from the ground up. What we saw is that if we use DERs and microgrids as the fundamental building blocks of the new grid, we can build a very clean, very resilient, and very equitable system. We do that by orchestrating DERs, and I'll go into the details of the technology during the presentation. But that's a key concept, right? We want to build systems from the ground up. And what we discover, what we learned, during at the beginning and during these years, is that these systems, system with distributed energy resources, are complicated and usually very rigid. And traditional solutions are not tackling the challenges to solve these main problems. These traditional solutions are usually centralized, meaning that there's usually one single central device that monitors and controls and optimizes everything from one single point, which are very customized and rules-based. They're vulnerable because there's a single point of vulnerability. I think, and the most important one, I think, is that it's hard to scale because, if you add more resources, you have to aggregate everything in one point, calculate how to integrate them into the system and start dispatching, but it needs changes, right? And you can synthesize these challenges in three main points. One is that, well, this system is not standardized, meaning that there's a wide range of technologies out there, and a lot of different vendors as well, and they all have different characteristics and different ways of doing things. And then the topology where the systems are built also change all the time. Also, point number two is that these systems are complex. You have to deal with a lot of different interactions between the resources, a lot of effects from the external world due to weather, grid, users consuming energy in different patterns. So this is complex. And also, we're talking about a dynamic environment, meaning that a system is not a rigid topology, right? So things might be added in the future, might be removed, some new technologies might be developed. Where, for example, right now in a very critical transformation in our energy sector, because electric vehicles are getting electrified, and that implies a big change in how we do things. We need now much more energy per house to be able to provide to charge those vehicles, and we need points where vehicles can be charged very quickly. So there's a lot of changes coming. And we discovered that if we take a different approach, we take a distributed approach to the grid, then things are much simpler, and they can scale much better. And the key concept is, let's put intelligence and decision-making capabilities at the DER level. Not a centralized point that makes all the decisions, but every single DER has decision-making capabilities. And by doing that, you end up with a system that is dynamic and it can respond in real time. So it's not rule-based. There's a single point of failure and self-healing, because you can remove and add things, and the system will continue operation. And the most important aspect that I believe this has is that it's fully scalable, and you can grow it significantly without adding a lot of complexity. Because as you add more resources into the system, you also add more decision makers, and that's the key aspect of this. Now, this is a concept, right? This is, let's do a distributed approach to the problem. But we wanted to have a product that we can offer to customers and that we can do projects with. So we came up with the Heila Edge end-to-end platform. Heila Edge is the solution that we use to build systems with this concept of distributed control and optimization. And the idea is that we have this device that we created, which we call the Heila Edge. And we install this device next to each DER in a system. So these devices can tie to the system, so these controllers can tie to the DERs, and then the collection of DERs start interacting and can act together. It can act as a single entity. They can cooperate to achieve common goals. We also have some support from the cloud, so we can run some of the things, some of the processes that are more computational intensive or that require more memory. We can run them in the cloud. We can offer also from the cloud remote access to see how the system is doing. And this has many advantages. The first one is that it's fully agnostic, right? You really don't care what DER, so what technology you're using. It could be a battery, a generator, solar, load control, electric vehicles, you name it. We have actually integrated with any of them. So you kind of like create an open field, a level field, right, for everybody to participate, which goes along very well with the concept of open source, right? You want an open level field so that people can really compete, and you don't have these vertically integrated solutions that stifle innovation. So this technology agnosticity, vendor agnosticity, and topology and architecture agnosticity of the system are key. You can have grid-connected system, islanded systems that can be combined and then separated. Since this is all using DERs as the building blocks, like Legos, you can just accommodate them very easily to wherever you want. The operation of the system is fully automated, and it's also very flexible and ready for the future, because you can incorporate all technology that you make intelligent with these devices with newer technology, and change and adapt as things change, like different rates and different technologies are included. Our product offering includes 4 main pieces. One is the hardware that I mentioned, the device. Although I have to say that the most important innovations that we have in the company are in the algorithms and the software, and the hardware is just a method to put them in the field. But we build our software to be able to run in any hardware. Our software includes algorithms to control, optimize, and orchestrate DERs, usually with economic dispatch idea behind. So that's usually the goal. We also have user experience where we provide dashboards and data. We provide alerts, analytical tools, etc. And also very important is that we offer the customer scalability. So you can build very large systems with this technology. Going more into details, here's a map of what our product hardware can do. The main concept of the product hardware was to build something that was very versatile, so we can go to any project and be able to connect what's there. So we wanted to offer kind of like a master of our trade, right? Like you can go and with analog signals, and you have sensors, communicate with all devices through serial, newer devices through Ethernet. You can control relays in dry contacts or read from them, and also connect to the internet, right? And provide a subnet for devices there. So we wanted to have something very, very versatile. So that's our hardware. The software includes many different pieces, right? To achieve the main, algorithms that I described above. So the software includes interoperability, and this is, by the way, I think where there could be a lot of collaboration to achieve something that is open source. There's a lot of different standards, and you can see names there. We have integrated most of them, some of them like very one-off implementations. These should all be available for anyone to use, in my opinion. so that you can just go and use your device and you're already compatible with all this. And I think some of the efforts of Linux Foundation Energy groups is regarding this. So I think there's a big opportunity, and it's a big headache for us, and we wish there was something there that we could just use, and we're happy to contribute if it's possible. The second main aspect that we do is control. So we can control a single DER. Here you can see a battery plus a solar, an inverter. But just as easy as we can control a single battery and a single solar, we can control multiple. So you can build very large systems. And really the complexity is more or less the same. There's not much different the complexity of the two systems that you're seeing on the screen. We can make them react second by second. Optimization, as I mentioned, is usually related to economic objectives. So demand charges, things like that. So when you have a system, you want to be able to minimize the payments, the energy cost, considering the constraints, right? You don't want to be breaking rules, or like if you cannot export, then you cannot do that. And also, extending the life of equipment. Data is a big aspect of this, and I think there's also a place where an open source effort could be leveraged. Because there's a lot of data out there, and people should have access to data to make better decisions. So again, leveling the playing field for everyone. We use the data all the time. What we collect, we transform to actionable insights in terms of efficiencies, in terms of response time, so we can know when to send the set points, etc. I think one of the most important aspects of any energy-related or so any system that has energy storage and that has to make decisions is forecasting. You have to be able to predict consumption and generation of energy. The other aspect of the software is the product interface, and we have dashboards for fleets where you can see all your systems. You can see a site where you can see the specific one specific system and see what the different all the different resources are doing. Some views to configure and customize. We use this with customers, and customers use them all the time. And also some tools for analytics. We offer our customers that idea of, hey, here's the data, you can process it and start understanding how things are operating and performing. This is the overall map of our product, including the dashboards, the cloud, infrastructure, the actual projects where we put things in the field with the Heila Edge devices and different types of projects, and how we can run things both in our hardware here and also in the cloud, directly in the cloud. And this technology can be applied to a lot of different projects. So we have done projects that are microgrids, meaning that there are multiple DERs behind one single point of common coupling and one single meter. So you coordinate internally to then go into the external world, or it can be that every DR has its own meter and you still coordinate. There are different operation paradigms, right? In one, you have your own decision to maximize your economic benefit, but then you are incentivized to deviate from that. And the other ones, everybody has together an economic benefit. So, but the algorithms, if they are distributed, can tackle both and can change from one to another if needed. Also, we have done CNI sites, commercial industrial sites, where there's only solar plus storage and load in one single location. And then we have also done sort of like merchant power plants, where there's solar plus storage and there's no load. So again, very flexible in where these algorithms can be applied. Here are some examples of some of the projects that we have done. We have, including behind the meter microgrids, including the Stony Farm microgrid that I mentioned at the beginning. It's in California, and that's where the company actually got started. That project is up and running. The customer decided to be off the grid, so we have been off the grid there for many, like couple of years, year and a half now. We have a project in Colorado and New Mexico, and these are, again, behind the meter microgrids. We also have front of the meter microgrids where the utility actually owns the equipment. There's really no difference between the two in terms of operation if you use this distributed approach. We have also done multiple CNI sites. We have two examples here. One is a wastewater treatment plant that is currently being retrofitted to have a microgrid. And we have done like smaller CNI type sites for different applications. And as I mentioned, also solar plus storage plants that don't have any load, but you can also control and make the decisions. Here are some a little bit more details about the different projects we have done with the technology. This is Thunder Swarm, and as I was mentioning, off-grid operation most of the time. This is the microgrid in New Mexico, which is actually inside an Air Force base. A microgrid that we did in Louisiana with the utility there, front of the meter system. And a microgrid that we're building in Tampa. All of this with the same concept of distributed control to achieve the common goals of the system. So with that, another example, and with that, I end the presentation. Thank you very much. Happy to answer any questions.